whole scene is driven by a series of mathematical equations. Hopefully you'll see some fish. Yeah, so there you come. So there's a shark. Again, the shark is a mathematical object here. And there should be some other fish coming along. So there's these little fish also. It's again the same equation but different parameters. You can see that they're moving. And you can see it's pretty realistic. And there are other things. So you can essentially just simulate this whole scene with a series of mathematical equations. And the thing is, it's still the same equation that I was talking about. I'm applying here, 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 and here, everywhere in this case. So this is another project where we were looking at face recognition. Now face recognition is very complex. Airport, you passport through, it will recognize yourself. You don't really need to show your passport to security anymore. So what we are looking is actually the next generation facial recognition. The next generation facial recognition is in 3D. So you basically scan your face. Here's my face scanned. This is the scanned face. You have a megabyte of data. Then you can reduce, you can take the features of this object, for example, nose tip, symmetry profile and things like that, and then convert this data into a smaller set, in this case 30 kilobytes. And then you can use recognition. So the recognition is based on things like symmetry profile. Now the symmetry profile is, if you look at your face, if you divide your face into two halves, the line essentially that divides the face into two halves is called the symmetry profile. Now this profile is actually unique. If you take identical twins, take this symmetry profile, they are different. But if you take a picture of them in 2D, of course they're not very different. So this is why we claim that 3D face recognition can actually recognize, has got higher recognition rates, because you can actually recognize even identical twins using this. So things like nose bridge, symmetry profile, eye center and things like can be used to do recognition. The other thing that we worked is, if you look at this is the 3D data capture from a 3D scanner. Now that's around a megabyte of data. Now imagine the whole of UK population, millions, and I want to save this data into a database. I'm talking about gigabytes here. But what we were able to do is we were able to reduce this data by about 30 kilobytes per person, 3D data. So that means I could actually take a pen drive and put all the UK population in my pen drive if we wanted. So from 1 megabyte to 30 kilobytes. So this is how much we can compress the actual data. This is another project we are currently working. We are looking at the sun. So we're trying to actually understand the sun in terms of space weather. So we are actually looking at 3D modeling of solar features, things like sunspots, active regions, and magnetic field lines. Let me just show you this video, which probably will show you some of the activities of the sun. So this is sun captured from a stereo satellite. So we have two satellites. Using those two satellites, you can actually track these features of the sun. So you can see some of the active regions, the sun. So this is the magnetic field lines and things like that. So why do we study sun? Because obviously for future space missions it's important to find out when these solar flares and eruptions would occur. It affects satellites if there are eruptions and solar flares. It also affects satellites, communication, and also aviation industry and power grids. So it's actually quite important to understand the activities of the sun. We can fairly well predict the weather on Earth these days. So the idea is to go beyond that and trying to predict the weather within the kind of solar system. So what we are doing here is we're trying to understand how the magnetic field lines distribution works when activities happen, and also other solar features based on the satellite data. We're trying to actually develop a predictive model so that we can predict these things in the future. This is some of the work that I'm currently involved in. It's a spin-out company from the university where we are actually looking at computer games. Why? Because it's a very big market. It has got about $8 billion in terms of the actual market in the area. So the idea here is, at the moment when people play games, they go to the shop, buy the DVD and put it on your Xbox 360 or whatever you want to play. But the idea is, in the future, that's not going to happen. In the future, what's going to happen is you will actually log on to some site, download your game, and play it. Even now, they have started. For example, Sony has got, you can go to Sony Online and download your game to your Xbox 360, but it takes, I don't know, 2 or 3 hours to do it. So what we are saying is, can we actually avoid all this? Can we actually let the person to play the game in real time? Let the game play somewhere on a server, and let's just play it, let's just allow the person to play. So that means I could even play the game on iPhone if I wanted. So all I need is just an internet connection, go to the site, and then download. Well, I don't need to download, I just play the game on the server. But to do that, you need to be able to transfer this data very quickly. So how do we transfer? So this is again using our technology that we developed. We are actually currently developing a platform here. So here, this is a model in computer game, but this model is not point cloud data. It is an equation. It's a mathematical equation, which can actually create any resolution as you like. So when the object is coming nearer, you want a high resolution. So it will automatically create that high resolution. When the object is far away, you don't actually need to render it at that high resolution. You can essentially represent it as a stick or something. So this is, you can see when it comes to high resolution, it increases. When it comes closer, it increases the high resolution. So similarly, you can look at other games environments. So if an object is very far away, you don't need to render the whole thing. So you can see there's a dragon somewhere there. So that dragon, when it comes near, we actually render it at a higher resolution. But the whole thing is actually controlled by a mathematical equation. So this is why we can control the resolution at any level we like with this technology. So this is a platform we are currently developing, and we don't want to actually, we already know our competitor. There's a competitor called OnLive, which basically delivers, they are actually prepared to deliver the games through video. So their idea is, you have a server somewhere, you play the game, you send a video stream to the, so if I had my iPhone, I could play it, but I only see a video stream of the game played somewhere else. But that's okay. So, but what you're saying is we're going one step ahead. And we will actually deploy this in probably 3-4 years down the line when OnLive and when everything is settled down. We'll try and deploy our technology into the market, and hopefully it will catch up, and hopefully we get a good segment of the market. That's our idea. Okay, this is another project that I'm currently involved with Singapore. So this is sponsored by Singapore Media Development Authority. And the idea here is it's called Singapore CoSpace. So what they're trying to do is trying to develop a virtual Singapore. So you go into this virtual environment, you can see what you see in Singapore in a virtual environment. Not just see it, but you also want to feel it. So if you touch something, you want to feel that this is how it feels. So if you touch, I don't know, a solid, you feel like it's a solid. If it's a liquid, you feel like it's a liquid. So we are involved in actually creating this kind of virtual environments where we can actually manipulate these objects fairly quickly and realistically. This is another project that I'm involved currently where we're developing a lie detector. So the idea here is when somebody is being interviewed in an interview scenario, you look at their facial profile. So you look at their eye movement, facial expressions, and can you actually tell whether this person is lying, just basically looking at the face. So this is basically our idea. So what we're trying to do is, you've got, this is one of my research assistants, just tracking faces at the moment. So basically we look at the eye movement, other facial expressions, and see whether we can get any cues. We also look at the thermal domain. Now the thermal domain is very interesting because you can see a lot of things that you don't see in the visual domain in the thermal domain. In the thermal domain, basically you look at the heat distribution of the face. When someone is actually lying, it is because someone is actually making up something that you haven't thought before in your brain. So that what tends to happen is your blood flow pattern increases around your eye level and things like that. So the thermal camera can actually measure these things and then tell. In fact, what we have just discovered is that when somebody is lying, their facial temperature changes by about 0.15 degrees. So if you can detect this, you can detect whether the person is lying or not. So let me just give you a basic background of how this thing comes up. This is a project